Evening, everybody. Hey, tonight I have a very interesting problem from the 2021 American Mathematics Invitational Problem Tournament, I guess. AIME, let's see, what is that? Oh, American Invitational Mathematics Exam. This is problem number 5. Now, this problem is just as much comprehending the English as it is doing the math. So the first part is going to be what I guess you could call a direct translation. We have to read through this description of the problem. Now it says, call a 3-term strictly increasing arithmetic sequence of integers special. They use the phrase special. Now these are integers, all right? And this is a mouthful of words, but it says if the sum of the squares of the first 3 terms equals the product of the middle term in the square of the common difference. Now, so just setting this up was a little bit of a challenge, trying to figure out what to do, how many variables to declare. But to minimize variables, I just chose the variables x and c. So this would be the first term right here, x minus c. These are all integers, remember. So x is going to be the middle term, and then x plus c is going to be the last term. And of course, c is the common difference here. And guys, for example, if you're not familiar with arithmetic progression or arithmetic sequence, like say x was 10, okay? Well, the first term here would be 7. The second term would be 10, of course, and the third term would be 13. So an arithmetic sequence is just a sequence where each of the terms is divided by what they call a common difference with the operation of addition. Now, so there's the way we're going to write it: first term, middle term, last term. All right. Now, so again, the direct translation part, okay, this is the square of the first term, right? It says it's equal to the sum of the squares of the 3 terms. All right, so this is the sum of the squares of the 3 terms, this piece right here. That corresponds directly to the sum of the squares of the 3 terms. All right, now they say that equals the product, okay? This very last piece right here would be the product of the middle term. We see x is the middle term, right? X is the middle term, there it is. And then it says the product of the middle term and the square of the common difference, which is this piece right here, okay? So everything's good, and I literally spent as much time on this part of it as I did the mathematics, directly translating the English into a terse mathematical statement. Now, I did leave out a little bit of the work here, but when you expand all of this out, you can see that you get x squared happening once, twice, 3 times. That explains the 3x squared you see right there. Now we catch a little bit of a break here because you will get minus 2xc when you expand this, but you'll get plus 2xc when you expand this. So the xc terms cancel out. And then notice that you would have a c squared term and a c squared term here. That adds up to 2c squared. And of course, we've already explained this piece right here. So this is the equation we're interested in right here. Now, it turns out, and it seems like there's too many unknowns here, but you do have a quadratic in the variable c right here. Okay, you have a quadratic. Well, the quadratic's actually in the variable x, but c occurs enough to where it can be used as part of the quadratic formula, meaning your minus c squared will behave like your b in the quadratic formula. And then of course 3 and 2c squared will be, 3 will be your a, and then 2c squared will be your c. And so here's the result of applying the quadratic formula to this. Okay, this line right here. Now, a nice thing happens right here. Notice that this looks kind of intractable, but you can factor c squared out of this. C squared is common to both terms, and when you take the square root of c squared, you get c, and you get left with the discriminant of c squared minus 24. All right. Now, for these to be integer values, c squared minus 24 has to equal to a perfect square. All right. That's the key part of the problem. Or we are looking for integer solutions, right? We're looking for integer solutions. These are all integers, and so we have to ensure that this discriminant, they call it, is equal to a perfect square. Now it turns out that 49 and 49 is a perfect square, 25 is a perfect square, 7 squared minus 5 squared gives you 24. And so you can kind of figure these out by just looking around for the smaller squares. Again, 7 squared would be 49. 49 minus 24 is 25, which is 5 squared, right? So the claim was made right here that 5 and 7 were the only ones that work, and that happens to be true. I'll explain that more at the end of but just for the sake of this, let's move along, and trust me on this for now, and then we'll show you why at the very end. You probably already see it, you know. But anyway, if you use c equals 5, you're going to get 30 over 6, and you guys can verify this. If you put 5 here, 5 here, excuse me, if you put 5 everywhere you see a c here, you'll end up with 30 over 6. For the plus side of it, now for the minus side of it, you would actually end up with a fraction, which we can't tolerate, right? We're looking for integer solutions. So the fractional pieces are we got to reject them, right? But we do get 2 integers, namely c is equal to 5. Okay, you would get 5 for c and 5 for x. And also right here, you would get 7 for c and 14 for x if you follow the arithmetic there. Okay, so what we know now is that we have 5 plus 5 and then 7 plus 14, right? And that's what the question was. It says find the sum of the third terms of all the special sequences, right? Well, this is the third term, right? And then there's only 2 of these so-called special sequences, right? You have one that involves 5 and 5, and another that involves 7 and 14. Okay, so let's go down to the next line here. Let's see, where are we? I must have skipped down too far. Yeah. Now, so finally, the sum of the last terms is what I just told you guys. It would be 5 plus 5, that first case, and then 7 plus 14. So this is the answer to the problem out here, 31. Okay, but I want to spend a little bit of time explaining why this only holds for 5 and 7. You probably already see it and probably just tune out, you know, right now. But notice that again, if you were to put 7 squared here minus 24, okay, you would get 5 squared, right? But notice that these are non-consecutive squares, right? And the claim is that these are the largest non-consecutive squares where this can happen, all right? Again, consecutive squares are separated by odd numbers. So we don't even have to worry about consecutive squares being a possibility here, because any pair of consecutive squares is separated by an odd number. For example, 36 minus 25 is 11. 49 minus 36 is 13, right? 81 minus 64 is 17, right? So it's clear that this statement, you're dealing with non-consecutives, right? And so non-consecutive squares. So let's look past 49 here. This is 49, this is 25, right? So if you get to 64, right? The next non-consecutive square, okay, you see 81 would be a consecutive square, and there would be 17, and that would be okay, but this won't permit a consecutive square. Now, once we get to 100, see, and you can see it's just going to be getting bigger and bigger. 100 minus 64 is certainly bigger than 24, right? That's equal to 36, which is clearly greater than 24, right? So you can see that's the argument. This isn't, I wouldn't call this super regular. We're not using congruences or anything like that. We're just kind of shotgunning this thing. But again, 5 and 7 are the only cases that hold up to this particular squared relationship, okay? And again, the solution to the problem is 31. All right, folks, let me know what you think about that one. I thought it was very challenging. There's no way I could have worked that. I had to look at some of the hints. I looked up some of the stuff. I made a little bit of progress, but I could not solve it without looking at some of the ideas. You know, I spent an hour on it, and it was close, but just couldn't quite get it without getting a few hints, looking up some of the solutions online. But anyway, thanks for viewing, and again, let me know via the comments if you have any questions.